Hi. In this video, we are going to talk about odd and even functions. Let's start with two functions, two really simple parabolas, a quadratic parabola and cubic parabola. So y equals x squared, how do we graph it? Oh yeah, we know it's a basic parabola going through the origin. And cubic parabola, in the first quadrant it looks pretty much the same, but then for negative numbers it's negative. Okay, so let's look carefully what happens here. If we take two opposite values of x, let's say 2 and negative 2. 2 squared is 4, and so is negative 2 squared. So we can write negative 2 squared equals 2 squared. If you use the function notation, let's call this function f of x. We can say that f of negative 2 equals f of 2. More generally, we call a function even if this is true for every x from this domain. F of minus x equals f of x for every x from the domain. This is the definition. Let's do the same part for the odd functions, and then we will continue to explore that. So also we'll consider two opposite values of x, 2 and negative x, 2 and negative 2. 2 to the third power is 8, but negative 2 in the third power is negative 8. So we can say that negative 2 to the third power and negative 2 and positive 2 to the third power are not equal. This is negative 8, this is 8. So they will be equal if you put minus in front. Or, using the function notation, we can say f of minus 2 and f of 2 are opposite. So this is what we call odd functions. If f of minus x equals minus f of x, or opposite to f of x, again, for every x from the domain. So this is the definition of odd functions. So let's look back, let's look at both of these definitions and the diagrams once again. So what this really means. If you take any two opposite values of x, their y values are the same. Left, right, left side, right side, no difference. Same values. In this case, we have a positive value for the positive 2 and opposite value for the negative 2. So they're not complete strangers, but they're not the same. They're opposite. They're opposite. That defines odd functions. Let's talk about the graphs of odd and even functions. It's pretty clear that graph of this function is symmetric with respect to the y-axis. And it will always be the case. We can draw some other even function, something that we don't even know the equation of, but as long as it's symmetric, let's say, let's make it a little fancy, something like that. Yeah, something like that. Whatever the x value is, the opposite value of it will have the same values of y. That's what symmetry really means. So we can say symmetric with respect to the y-axis. In this case, we are going to draw some weird function also, such that whatever happens on the right side may be something like that. On the left side, we have everything opposite. It's harder to draw, something like that. So when you have x value here and opposite x value over here, their y values are also opposite to each other. So this type of graph will be symmetric with respect to the thing. to the origin. It's a point symmetry. This point will be reflected here. This point will be reflected here. This point reflected over here. So it's a central symmetry, point symmetry. So let's continue looking at other functions besides basic y equals x squared and y equals x cubed. So these functions are nice and actually easy to understand why we call these functions even and odd. Even degree, odd degree. But what about other functions? It's easy to figure out that all functions with even degrees will be even, and so on. And all functions with odd degrees will be odd. Oh, including x itself, because this is x to the first power. And if you think about these graphs, the graphs will all look like the basic function. This will be parabola for all even degrees, and this will be parabola for all odd degrees, or y equals x will be a straight line, and all of them are symmetric with respect to the origin. But it doesn't have to be just a power function to be even or odd. Those weird functions I drew on the previous screen, they're not just x to some power. I don't even know the equations, but they're clearly even and odd. You don't know that many functions, but you know this one, for instance, y equals absolute value x. And the graph of it is symmetric, as you know, with respect to the y-axis. And no matter what x is, positive or negative, opposite, the value will be the same. There will be other functions that you're going to learn this year, basic functions which are either even or odd. But the truth is, many more functions are neither even nor odd. Something like this, maybe you can draw, whatever. It's not symmetric with respect to the y-axis or nor with respect to the origin. So we know now how to determine more or less if a function is odd or even or neither just by looking at the graph, if it's symmetric in either way. But if you don't have a graph, we still should be able to determine if it's odd or even or neither algebraically. Algebraically means just using symbols. That's how we do it. So if this is f of x, we want to compare it with f of minus x. So that's what we need to set up. What is f of minus x? So first we plug in minus x instead of x. Everywhere we see we see x, we should replace it with minus x. Just x itself, plus 7. And then we simplify it. Negative x raised to the 6th power. The 6th power itself is an even function. So it really doesn't matter, positive or negative x, the answer will be the same. Same is true for 4th degree. So we still have a minus, we still have a 3, but negative x to the 4th becomes x to the 4th. Absolute value function is even, so absolute value of opposite x and x, they are the same. And 7 doesn't care, we're not plugging in anything. So if you compare these two, we can tell that f of minus x is the same exactly as f of x. So that gives us conclusion that it's an even function. Let's look at the next example. Let's call it g of x now. Same approach. In order to determine if function is odd or even, we must compare g of x and g of minus x. So we are going to set it up. Be careful with the signs. This minus is just here. Instead of x itself, we need to put minus x and then raise it to the 5th power. Plus 4. Instead of x, we put minus x. Minus, instead of x, we need to put minus x. And now we simplify. So minus x to the 5th power itself, the 5th power is odd degree. So it will change the sign to minus x to the 5. But we also have minus in the front. So what is tricky here is that this turns out to this. But minus is just waiting there. Minus is not raised to any power. This minus, I mean. Okay, now let's continue. So plus 4 minus x cubed becomes minus x cubed. So what happens here when you raise anything to the third power negative, it remains negative because x cubed itself is an odd function. And this is easy. This is negative, negative, so it's just a plus. Let's simplify a little bigger, a little more. So this is now negative times negative something, so it becomes positive x to the fifth. This positive times negative, so it's negative 4x cubed plus x. So let's compare f of x, g of x, and g of minus x. So the first term becomes opposite. The second term is opposite. The third term is opposite. So what we found is that g of x, g of minus x, is completely opposite to g of x. That tells us that it's an odd function. I'm going to preserve our results and look at one more example quickly. So we are going to look at h of minus x, substituting x with negative x, substituting x with negative x, and 5, nowhere to replace x with anything. So we simplify it, it becomes opposite x cubed plus x plus 5. So when we are going to compare these two functions, we will see. So this turned to opposite, this turned to opposite. Ooh, but this did not. So we cannot say that either h of minus x equals to h of x, or h of, so that's not true, or h of minus x equals to opposite h of x. They're not equal, they're not opposite. Therefore, this is the case when it's neither odd nor even. All right. So now let's look carefully. Maybe there is a shorter way to determine if a function is odd or even or neither. The truth is, we need to know how to do this. We need to know how to do it algebraically, this whole thing that I just erased. But in many cases, we may just look at the function and tell right away. So look carefully, and you can see that in the first case, the polynomial has all even degrees. Oh, this is not even a polynomial, but it's an even function. 7, guess what? You can look at this as a polynomial of a 0th degree, because we can write it like this. Or we can also look at this as a constant function, which has the graph y equals 7, which is symmetric with respect to the y-axis. So yes, y equals 7, or any constant function, is an even function. In the second example, we have odd function, odd function, odd function, because x is first degree. And in the third case, we have odd, odd. It's an odd number, but it's an even function. This example could easily be y equals 5. It's a constant function. So we can create a shortcut, two actually. One shortcut is for polynomials, the other is for any combination of functions. Okay, so think for a moment. A polynomial is an even function if all degrees are even. And the polynomial is an odd function if all degrees are odd. So what if it's not a polynomial? What if it's just any function made of other functions? Okay, so if you add only even functions, like in this example, then the result will be even. If you add only odd functions, like here, the result will be an odd function. And if we mix them up, like we did here, odd, odd, even function, then it will be neither. There are rules. Oh, when we say sum, it can easily be a difference, of course. And there are also rules for product and quotient, which It's not that important for us now, but try to figure it out too. If you multiply two even functions or add functions or add an even, what will happen as a result? All right, that's it.